All right, good morning everyone. So I see almost all of you completed project 0, so that's great. So I think Anshu, our TA, is going to pair you up this morning, so that like you can start working on project 1. All right. Okay. So in this lecture, we're going to continue last class. And the main goal of this class is to extend what we discussed in one-dimensional space into two-dimensional space. And that gives you a great position to start on the project. All right, so before we do that, let's finish up what we discussed last lecture. So in last lecture, we first of all derived tau, the truncation error. The truncation error is an error that is associated with discretization. It is basically the difference between my AU minus partial square U partial x square. So it is the difference between a finite difference approximation to a differential operator from the differential operator itself. And then we discussed that if I define the solution error to be the difference between U minus U hat. So this is the analytical solution. This is the exact solution, let's call it. And this is my numerical solution. Then I have a relationship between between E and tau as A times E equal to, I always mess up with the sign, but it is either plus or minus tau. All right, and that means the solution error E can be bounded by the norm of A inverse times the norm of tau. And because we know that tau decays at an order of accuracy that can be analyzed from the Taylor series. Right, so we know from Taylor series how fast does tau decay as I make my delta x smaller. So if I know that the norm of A inverse does not depend on delta x, then I know that my solution E is going to decay at the same rate as the rate at which tau decays. So the stability we have been trying to analyze, that means the norm of A inverse is bounded from above by something independent of delta x. Okay, that's the stability we want. If we have that stability, then we know my solution error is going to decrease as I make my delta x decrease. Otherwise, it is not guaranteed. Otherwise, even though I may have a great finite difference operator, my solution can be garbage. And I think you are going to see that in your projects. Okay, so last time we have analyzed that the norm of inverse A is bounded by something that looks like this. That looks like delta x squared divided by e to the delta x divided by delta x pi. What was that? Actually, sorry. Was pi divided by n, right? Minus 2 plus e to the minus pi divided by n. Right? Okay, so that's, yes?
It's not the exponential, it's the exponential times the imaginary part, right?
Yes, imaginary part. Thank you. All right, very good. Good memory. All right, So that means we have delta x squared divided by the exponential I pi over n is equal to cosine of I pi over n plus an imaginary part, which is going to cancel with this one, and minus 2 plus another cosine of I pi over n. Alright, and both of these exponentials have an imaginary part that is exactly equal to the opposite of each other, so they cancel. And when you write it, it's delta x squared times 2 times 1 minus cosine of pi over n. Sorry, there is no I here. The I is already dealt with by expanding this exponential into cosine and sine. Okay. Now, can somebody tell me when my delta x shrinks? And at the same time, if I keep the same domain size, right, which means delta x times n is fixed. Let's say delta times n is the domain size, right? We have a delta x being the distance between two grid points, n being the number of grid points. So L is the total domain size being fixed. Then what is the limit of delta x goes to 0? Delta x squared 2 times 1 minus cosine. So instead of pi over n, I'm just going to write pi times delta x 1 divided by n divided by L, right? Because 1 over n is equal to delta x divided by L. So how can we figure out that limit?
L'Hopital's rule.
Huh?
L'Hopital's rule.
What rule?
Using L'Hopital's rule, it's like finding the limit of this. Like you have numerator, you have different, you have denominator. Just do the derivative, finding the limit.
Okay, doing the derivative. That's a very good point. It is actually, this is equivalent to using Taylor series.
Oh yeah.
Right? Basically, we can use Taylor series. We can apply Taylor series expansion to cosine. Okay, if we apply Taylor series to cosine as delta x goes to 0, we are going to see cosine pi times delta x over L is equal to, what is the first term?
1.
Is 1. What is the second term?
Minus.
It's minus sine of 0. Right? So the derivative of cosine at 0 is equal to 0.
So it's the square of it's 1/2 the square of
Okay, then the second non-zero term, you're right, is the half of, well, is the half times delta x squared times the second derivative of cosine at 1.
it's a minus.
Which is minus 1, exactly. It's minus cosine at 0, minus 1. And then plus O delta x to the cube. It is not delta x, actually delta x times pi over L square, because this is my coefficient. All right, now if I take this, if I substitute this, 1 and 1 cancels out. What I get is delta x squared over the half also cancels out, over delta x times pi over L square, right? And that gives me L square over pi square. So what does that tell me? That tells me this the largest, the norm of A inverse approaches some number that is independent of delta x as I shrink my delta x. Okay, that means the maximum norm of delta of A inverse as I shrink my delta x is going to be bounded. All right. So it is basically we want to make sure the norm of A inverse is not growing larger and larger as we make delta x smaller and smaller, and that gives us the property that the norm of the solution error is going to shrink at the same rate as the truncation error shrinks. All right, any questions? Yes.
So the solution will depend on the on L, right?
The solution.
Depend on L.
The solution depend on L. Yes, the solution depend on L. Right.
So if I have like different domain.
Yes, if you have a different domain, the ratio between the solution error and truncation error is going to be different. Actually, not only does that depend on the domain, it even depends on the boundary condition we are going to see. It depends on the equation you're solving, it depends on the boundary condition you apply, it depends on the shape of the domain, the size of the domain, it depends on everything. We only want to make sure it does not depend on grid refinement. So for a fixed problem, we want to make sure as we refine the grid, the norm does not increase as I refine the grid. All right. You also have a question?
So far, does the stability analysis restricted to elliptic system? Can this be expanded to like hyperbolic system, parabolic system?
Good point. This particular analysis is restricted to the Poisson's equation.
Okay.
Right. But you can use very similar approach for other equations. So here I have the inverse, the norm of inverse A, right, where A is the operator in Poisson's equation. But you can do a similar analysis if A is in another equation, and you can. So basically, the approach is look at what is the eigenvalues of the matrix A, and figure out like what is the maximum norm of A inverse.